He also serves as the co-director of Clinical AI at Stanford Radiology and is the Associate Director of Research and Education at the Stanford A&E Center. Welcome, Akshay.
Thank you so much. And thank you for all the organizers for setting up a fantastic session. And thank you for inviting me to speak here. Hard act to follow. But hopefully for the next 20 minutes or so, I can describe to you some of the work my group has been doing and really trying to work together with the broader community in maybe one of the narrower aspects of healthcare, which is focusing on radiology. And radiology has really been a large research interest because most of the computer vision research in healthcare really started with the medical images acquired within radiology. And initially, most of the work really focused on computer vision. But these days, we can't really leave language out of a lot of these works. So hopefully I'll try to describe how we can use language to better learn representations for computer vision problems and actually use language to be able to create things like synthetic data and actual language outputs to actually help in the workflows that radiologists are using. So just a little bit of a preview for the talk. Oops. Okay, here are some disclosures, none that will really affect the content of the presentation. I'll mostly be talking about some open source work that we've published already. So if we take a look at most computer vision models that are being used in radiology, things that include FDA-cleared products, tools that are being deployed in hospitals that are developed by themselves, we'll really notice that all these tools really focus on bespoke problems. So let's say if I have a medical image and I want to solve a classification problem about learning whether or not there's an abnormality, I'll use some sort of off-the-shelf model and then train it with my given data set to be able to say yes or no, there's a particular diagnosis. So that's one type of problem. But then if I really need to be able to understand and localize where on the image we're solving that problem, we need to build a different detection-based model. This might use the same training data, but we need to use a fundamentally different architecture to be able to generate these outputs. Maybe I want to solve something like a segmentation problem where I want to delineate very specific anatomy on the image. We might still use the same underlying images, but because of the difference in labels, we might use a completely different neural network. Even if we're trying to solve regression-based problems where I want to go from an image which was acquired very rapidly, and because of that, it has artifacts, and then we want to retrospectively clean that image up, we'll still use the same data set, but we'll have to train a completely new model. So here we can really see that most tools that we're building really rely on these bespoke solutions that are not really scalable, and they don't really leverage the insights that different tasks and modalities have. So obviously it comes as no surprise that there's a lot of potential for current generation foundation models to be able to aggregate some of these insights. And I really don't need to go into too much detail for this particular group, where with foundation models, we can curate large amounts of unlabeled data sets and build different self-supervised learning algorithms to train these foundation models, which can be adapted either in a zero-shot manner or in a few-shot manner to solve a variety of different downstream tasks. And initially, when a lot of the foundation models we looked at, they really looked at language as the binding agent across multiple different modalities. But Vivek did a great job describing how a lot of these foundation models can really be natively multimodal. And that's what we'll really be focusing on, really trying to understand how language can actually help the representations that we can extract for vision-related tasks. And I'll briefly just summarize a study that we performed last year that really looked at how language models are actually capable in interpreting medical text. I won't spend too much time because I think Vivek did a great job describing about how these language models do have fantastic capabilities in the understanding of text. But for this particular study, we primarily looked at this task of summarization, where we have some long context input that we're working with, and we want to be able to summarize salient insights in a condensed manner. So all the information is in that initial input. We just need to be able to bridge that down to something a physician can consume. So, we performed the study, almost 18 months ago, so I'm almost embarrassed to show what sort of language models we use, but these were state of the art when we were using it. But really, we wanted to look at different open source and closed source models that were trained in autoregressive manners or text-to-text manners. And we really wanted to focus on how do we adapt these models too for tasks of interest. And adaptation could happen for these open source models where we have the weights available. So we use techniques like low rank adaptation to actually fine tune them to our task. But even for the closed source models, we're really interested in adaptation, where we really explore this notion of in-context learning, where we provide examples within the prompt itself too, and really try to figure out what are the best types of examples to provide, what are the scaling law curves that we get by providing different amounts of information. I won't go into too much detail over there, but we really notice that in-context learning really helps the performance of these particular models, especially in this notion of out-of-domain data, that we don't necessarily have to do any test time tuning, but we can actually do tuning via the prompt itself. And we wanted to apply this for a variety of different healthcare tasks. So we looked at things like radiology reports, we looked at progress notes. So these progress notes use a lot of EHR-based data, a lot of subjective and objective observations about patients. We looked at patient-doctor dialogues, which I think are becoming very important these days because, at least in the US, you'll be hard-pressed to find a hospital that isn't wanting to use an ambient scribe to be able to save physician time. I think that's the initial claim, but really the value proposition that a lot of hospitals are seeing with these ambient scribes is how can we do better diagnostic coding to be able to increase revenue of hospitals. So it's interesting how the academic work can actually translate to what a hospital finds valuable, but I digress. And then when we had these different models and different adaptation methods, we performed a broad quantitative validation using conventional metrics, but knowing that most metrics for natural language generation are insufficient, we really wanted to be able to conduct a clinical reader study with 10 expert physicians to really understand, do these problems help solve, do these methods solve problems that these physicians face? So what we did was we picked the best model and the best adaptation method, and we were a little bit surprised that even off the shelf GPT-4, where we packed the entire prompt with in-context examples, worked the best. And what we really wanted to do was conduct an A/B study where we provide our physicians blinded examples of clinical summaries generated by the language model and clinical summaries actually generated by humans during the course of clinical practice. And we asked our readers to rate these in a completely blinded manner across 3 different dimensions, really focusing on completeness, correctness, and conciseness. And a lot of the reader study work that we did was really inspired by some of the nice work that was done in MedPalm before this too. So shout out to that work. And overall, we really just wanted to understand whether our human physicians preferred the summaries that were generated by humans or they preferred the summaries generated by our language model. And initially our hypothesis was, wouldn't it be great if we end up somewhere in the middle where there's no strong preference and that most of these summaries are really just interchangeable between these 2 groups. But to our surprise, across all the tasks, we saw that both for completeness and correctness, our 10 expert physicians at Stanford always ended up preferring in a statistically significant manner the summaries generated by the language model. And interestingly enough, this did not come at the cost of conciseness. So in the same number of tokens, in the same number of words, the language models were actually able to better convey the medical information that was relevant to be able to perform the next clinical action. So this for us was at least a really eye-opening moment to show that these language models natively have the capability to parse medical text. So this just made us think about what are some of the future applications one could think about, and especially how might we be able to apply this to computer vision problems, because that's my bias, is being able to solve some of these vision-based tasks. And over time, we really just had a hypothesis that language can really serve as a really strong prior for image representation learning. And again, for this particular group, I don't think you need too much description here, but the 2 methods I'll really be focusing on is using language to supervise our image encoders, using methods like CLIP. I'll give a very quick overview. We can have some text embeddings that we get from a large multimodal data set. And whenever we have all these text embeddings, we can also complement them with vision embeddings passed through any arbitrary image encoder. And once we have these embeddings, we basically want to maximize the overlap that these embeddings have in terms of your favorite overlap metric. We typically use metrics like cosine similarity, but there's different regularization you can do to be able to make this a little bit more scalable, different flavors of SIGLIP, et cetera. But that's basically CLIP, where we're using this text information to better train an image encoder. So that's CLIP. And then the other method that's very common for multimodal large language models these days is this notion of BLIP or LLaVA, which is basically bootstrapping language image pre-training. where now the goal is, rather than using language as an input, can we actually have images as an input and language as the output? So one of the tasks we might work with is taking an image in, and we have a specific query about that image, which in this case might say, write a romantic message about this photo. And then we want to be able to reuse different components of different models that we're working with already. So let's say we want to reuse some pre-trained image encoder, and we want to pre-use some language model which has been trained. Well, to be able to solve this text generation task, what we can do is we can just create this triplet data set where we have our input image, we have our query, and we have our answer. And we're just training a little adapter module in the middle. And this adapter module could be as small as like a small two-layer, multi-layer perceptron. And we can reuse a lot of these pre-trained components, which have been aggregated already, to be able to solve this language generation problem. So we really wanted to be able to leverage this specifically for medical imaging. And one of our first attempts towards this was this notion of a checks agent model that we're able to build. For this particular model, we just compiled all the chest X-ray images that we could from the internet, and we're able to compile this triplet data set, where that data set looked something like this. Each image would have, I'm missing my mouse pointer, yeah. Each image would have some sort of query associated with it. So for example, with this particular chest X-ray, we might ask a query, where's the opacity located? And we can come up with an answer in free text. And we're able to do this with the entire, with around like 6 million or so instruction examples. And then we took some open weight language model and adapted it in the mechanism of blip that I described previously. And then we adapted it for a variety of different tasks. I won't really go over all the tasks that we evaluated, but I really wanted to go into a little bit more depth for one particular task that we looked at, which is this notion of directly generating a radiology report from the images. And this has been a long interest because out for the field, because this is what radiologists do. That is a product of their work. They interpret images, they interpret these images in the context of a patient's medical record, and then they output all the findings that they see on the image and what the clinical diagnosis might be. But we really wanted to see how could some of these systems actually work in a clinical settings, and what are some of the gains that this system could have. So we conducted a reader study to actually see this, where we would start off with a set of images, and as a first pass, we would have residents read these images natively. This is how radiology works in academic medical centers, where residents take a first stab at generating radiology reports, and then the attending radiologists fine-tune the reports that the residents have drafted. So in one group, we had residents alone, and then in another group, we had residents that were using this checks agent model as a guide in generating the original reports. We timed how long it took these two groups to be able to generate the first draft report. And when we compared the residents working alone to the residents working with this checks agent model, we saw a substantial improvement in time. I wouldn't necessarily take these numbers as gospel because we're not using this in a clinical environment. So the absolute values of these numbers might change, but the fact that using some sort of pre-drafting aid improved the efficiency was a really good positive signal for us. And then next, once these reports are generated, we would have attending radiologists actually evaluate the final draft and whether or not this was efficient. And we noticed that attendings would take no difference in time to modify this. So this was another clue to us that just because residents are working with these checks agent drafted models, there's not particularly any harmful or erroneous information in there. So this was a really good first sign for us that these models right now have the capability to improve efficiency in clinical workflows. But we don't just want to go faster, we also want to be better, or at least as good as radiologists. So we similarly asked another question, whether the report generated by the checks agent model actually answers the reason that the imaging was ordered in the first place, so the indication of the exam. And overall, we found that the residents rated the checks agent somewhere around 5 or so. So that would say that on average, the residents agreed that the report is actually answering the question that the image was ordered for. Then we also had attendings rate the checks agent model, and the scores were a little bit lower, and this makes total sense. If you're more experienced, you're probably more critical, you're more knowledgeable. But on average, everyone still agreed that these reports worked well. And just as a calibration, we asked our attending radiologists to also rate our resident radiologists, and we're still within the same ballpark of images, of quality. So this for us was a really good first sign that a lot of these methods can actually be beneficial in clinical settings. So here I describe this notion of vision language models where vision is the input and language is the output. And with a lot of the methods that we're working with right now, this can actually be flipped upside down too, where language could be the input and vision could be the output. I only have one slide to talk about this. But what we effectively did was we can take some open source models such as stable diffusion. They're trained with these latent diffusion models where you can use text prompts to be able to generate images. And then if we just natively prompt some of these open source models with something like a photo of a lung X-ray with visible pleural effusion, you get something that's cartoonish. But even by fine-tuning this in a completely self-supervised manner, we can actually get really high-quality images just using language as an input. And we described how these generated images can really stay true to the input prompt. In fact, these images understand the difference between small abnormalities and big abnormalities, right-sided versus left-sided. It understands bilaterality and negation. So we were very surprised to see the quality of these models. And it was really nice that the first author of this work is actually a thoracic radiologist who could verify whether or not these images that were being generated are realistic. And we showed that by using synthetic data, we can actually patch for gaps that our models trained on real data can have. And using different approaches like self-supervised learning or targeted pre-training in a supervised manner, we can really improve the capabilities of a lot of models that are trained on just real data. And we have a new preprint that's coming out that will describe some of those methods over the next few weeks or so. So right now, hopefully, we're seeing that language can add a lot of value to our computer vision tasks. But the examples that I've provided so far are only examples of 2D imaging, so these radiographs. Radiology is much broader than just chest X-rays. Most of the challenging problems that a radiologist deals with are using imaging modalities like MRI and CT scans. And then secondly, the challenge with those more complex modalities is that the length of the reports that we're working with are substantially longer. So if we take a look at methods like CLIP, most of the captions that CLIP has been trained on have sequence lengths around 50 to 100 tokens. But when we look at some MRI scans or CT scans at Stanford Hospital, the average report can be upwards of 500 to 1,000 tokens or so. So really understanding the fine-grained relationships between language and images can be pretty challenging. And I think we need to be able to solve some of these problems to be able to impact real change in radiology. So for us, this was really the inspiration to be able to train this model that we called Merlin, which is a natively vision language model that works on 3D images in a vision language setting for abdominal CT scans. And we chose abdominal CT because this is the most common volumetric imaging test performed globally. In the US, roughly 20 million or so patients get an abdominal CT scan per year. So the scope of this problem is really large, and we wanted to see what are the capabilities of next generation models that we can actually have to solve this clinical problem. So here, we trained our model on around 16,000 CT scans and their corresponding radiology reports. And we're also able to pre-train this with EHR-specific data. So we looked at ICD codes, which are diagnostic codes that are assigned to patients for different diseases or different illnesses that they might have. And then we're able to evaluate this on around 5,000 data sets from Stanford and around 7,000 data sets from an external partner. So I'll very briefly talk about how we performed this particular training. So for the first stage of training, we would just take our full 3D CT scan and just train an image encoder to be able to predict the diagnosis code that the patient came into the hospital with. And we don't necessarily care about this task too much. We almost think about it as some sort of self-supervised learning, but we saw much better signal by pre-training for this particular task than your native masked autoencoder or contrastive learning methods. And then once we have this image encoder trained, we can now leverage the radiology reports that we have using our CLIP style methods. And we had to make a few adaptations to make CLIP really work for these high dimensional images. For example, if we just take our full 3D CT scan, which has image dimensions of around 512 by 512 by 400 slices or so. So there's a lot of complex medical information. And our CT scans are around 500 or 600 tokens on average. So we came up with different strategies to be able to take large radiology reports and be able to condense them into smaller groups. And that is what allowed this clip training to actually converge. And then once we trained this model, there were a variety of tasks that we can perform in a completely zero-shot manner. So some of the tasks we could do here was this notion of zero-shot findings classification, where we can just prompt in natural language for different findings that actually exist in a given image, and be able to understand whether or not those findings are represented in that scan. We can do things like phenotype classification, which is being able to predict the ICD codes. This can have some coding and billing implications that a hospital might really care about. And we can do things like zero-shot retrieval too, where we can retrieve other similar images based on just the image content, based on the text content. And this can have a lot of implications, especially in oncology, where our oncologists and surgeons really care about finding other similar patients that they or their colleagues may have treated previously and really understand, well, this patient had this particular outcome, and my patient is kind of similar to this, so what sort of outcome might they have? So this retrieval task can really help guide future treatment. And then we also evaluated a variety of different tasks with fine-tuning too. So we're able to perform tasks like opportunistic disease prediction, which basically says that a patient who is healthy today, what is the likelihood that they'll go on to develop a future disease where we have targeted intervention? So we worked very closely with our cardiologists, we worked very closely with our hepatologists to be able to define some of these tasks, like what is the likelihood that a patient will develop osteoporosis in the future, or they'll develop atherosclerotic cardiovascular disease in the future, because if we detect that early, we can actually intervene sooner. We do things like radiology report generation using methods like BLIP, and we solve our usual tasks like segmentation. I won't go into all of these results, but I'll just share some of the results that I find particularly exciting. So one of the tasks that we're very excited about is this notion of zero-shot classification, where we asked abdominal radiologists, what are roughly 30 of the most common abnormalities that you see on CT scans and that you care about? And we're able to come up with a list of most of these. And then what we did was, first we evaluated something like a biomed clip model, which is natively trained on image and text pairs. That's done in 2D, so we actually had to adapt it to work in 3D. And we saw a relatively reasonable performance. And note here, we're looking at F1 scores, not things like AUROC, because most of these findings are pretty rare. And if we go back to Lena's talk, we really need to be able to use the right metrics to understand what is clinically relevant too. And then when we actually look with our Merlin model on our internal data set, we see surprisingly high F1 scores ranging from 0.7 to 0.8 for a variety of these findings. And even when we apply this to external data that write radiology reports in a completely different style, have completely different patient populations, we see surprisingly high performance still. So we're quite excited about what the capabilities of some of these models could actually have. And then what we did recently was we actually compared this to larger models too. So recently there was a model released from Google, the CT Foundation models. There's not too much information about it besides the blog post, but there's around 25x more data that was used to be able to train that particular model. And we see that for things like findings classification that exist in a radiology report, we're on par. And then for things like trying to classify phenotypes, we're substantially better. So I think there's some lessons to be learned that just scaling doesn't necessarily help. I think thoughtful scaling can be very useful, and really knowing what are the best underlying methodologies to train our models can be quite vital. Maybe I'll skip this next slide for the sake of time. The other thing I really wanted to look at is this notion of segmentation performance too. There's been a lot of interest in this community, in the MICAI communities, to be able to train segmentation models, and there's a lot of specialized architectures that work for those. And we showed that with our Merlin model, we're more or less on par with this. I would personally still use some of these models like NNUNet because they're easy to train, they work out of the box. But it was really interesting to see that we see comparable performance across a variety of different large and small organs. And I especially want to point out that performance of these models, which are very easy to train like NNUNet, et cetera, can be very good in the first place. We've actually previously used models like NNUNet to segment different tissues on CT scans. And some of the open source algorithms that we've built actually have even received FDA clearance recently. So I think the point that I really want to emphasize over here is it's not always necessarily valuable to be able to improve your DICE score by 0.01 or 0.02, but really understanding what is a clinical task of interest and just understanding how good do you have to be for something to be good enough. And I think this is a common problem that I end up seeing with a lot of companies that we work with too, that sometimes the technical innovation isn't the limiting problem. It's the clinical implementation, it's a clinical workflow that really stops some of these tools from working in the clinic. So that was just a little bit of an aside. And then the last point that I'm super excited about is how much time it actually took for training this particular model. And we're super excited that we're training on around 15,000 scans. Our validation data set was 5,000 CT scans. And we're able to do all this training on a single A6000 GPU in less than a week or so. And if you want to figure out how to do this, I think the student who did this training, Ashwin, is in the back, so ask him all the hard questions you want. So hopefully, there's a lot of exciting work that's happening over here, but I also want to give a preview of where should we really be thinking about going forward as a field. Hopefully language can be really useful to learn better computer vision tasks too. But really, just because something is technically innovative doesn't always make it clinically useful or clinically interesting. So just being able to talk to the clinical stakeholders, understanding how your new risk model will actually work in a clinical setting, who will pay for that, who will value from it, what is the life cycle? Those are the questions that can actually allow things to succeed in the clinic. And the more we learn about that, I think the better it can shape our work too. And I think we're preaching to the choir here, but for all these new technical advances that we come up with, I think there's just a need for large amounts of high quality and rigorous evaluation. And I'll just give a little bit of a preview on evaluation. One of the things that's hardest to evaluate is free-form text. And we've been happy to be able to develop some of these metrics, like green, for example. Green is basically trained by distilling a frontier model for the specific task of evaluating the quality of radiology reports that are automatically generated by models. So not only does this provide you with a quantitative score, but it also gives you a qualitative understanding of where is your model making mistakes? What are the types of these mistakes? Are they clinically significant? Are they clinically insignificant? Are they style-based? And there's a lot of metrics like this too. And I'm sure Pranav might talk about some of these metrics in this talk too. There's no right or wrong, but just using some of these tools can really just improve a lot of the models that we're working with. And lastly, I think maybe based on the Q&A from the last speaker too, we like open sourcing everything that we do. So our Rentgen model, which is our text-to-image generation model, can be found here. Checks agent model, including all the pre-training code and the trained model weights, can be found here. We now recently open sourced our Merlin model too. I think it's been downloaded close to 100,000 times on Hugging Face too. And I think what's most exciting for me is with the Merlin model, we'll actually be open sourcing our data set too. So this will include 25,000 CT scans and all the corresponding radiology reports. At Stanford, whenever we open source data, it has to be manually reviewed by a human to make sure that there's no PHI in there. And we finally just finished the review of 25,000 images and 25,000 reports. So hopefully that'll be soon to come. So maybe I'll pause. I'll stop over there. Happy to take any questions. But before I do that, I just want to thank the fantastic group and our funding sources that actually enable this work. They do all the hard work, and sometimes I have the benefit of being able to present for them. But yeah, just a shout out for all the great team that we have and open to questions. Thank you.
Thank you, Akshay. That was a fantastic talk. And, it's incredibly exciting to see that even models at smaller size can get such impressive results. Questions, please. Please raise your hands.
Very quick question. Your segmentations were zero shots or into fine-tuning?
It's fine-tuned. Yeah.
Okay, there's one more.
So,
on the clinicals, can I ask the question now?
Just give us a moment.
Okay.
Yeah, I think we'll do in-room questions for, okay, yeah.
So you did it for the radiology one. I was thinking like to do the same thing for the histology, the moment you have the report from the pathologist, you do the similar stuff, and how would that translate?
Yeah, so I don't do too much pathology, so I don't have too many educated opinions over there, but the workflow is pretty similar. There's different challenges that most of your pathology images are just very high resolution. We actually will be presenting some of this work at Middle. We've been able to train some medical VAE models that allow you to compress images. So instead of working on your natively large images, you can actually train models based on a compressed latent representation. And this latent representation can allow for compression on the order of 20 to 50 fold or so without a loss in downstream accuracy. So if we had to do some fully end-to-end pathology report generation models, that might be an approach that I would start off with. And I know there's a lot of fantastic work in pathology going on too, but maybe I'm not the expert there. Yeah, but similar workflow.
Please go ahead. You had a question.
Yeah, sure. Your talk is amazing, Akshay. And given the large scale use of medical images and reports, how does your lab think about the privacy preserving training? We are currently exploring differential privacy in UFM3R project. Do you see this is promise in combining this path with federated learning or synthetic data augmentation?
Yeah, that's a good question. And I'll maybe let Daniel talk about differential privacy later. I'll punt that question to him. But I think these are relevant. We've been exploring the use of synthetic data as maybe one way to be able to overcome some of these challenges too. If we can not only train on synthetic data sets to save patient privacy and at the same time be able to patch selectively for bad performance of supervised models, maybe we can have our cake and eat it too. But I know, especially with things like differential privacy, there's a lot of methods that still need to be able to optimize to get to the same level of performance that we're seeing. So I think maybe still more work to be done there.
Okay, thank you.